It's defined by an plus 1 is equals to 3 plus 2 into an divided by 2 plus an for n bigger than or equals to 1, and where a1 equals to 1. Which of the following is true? First one, n is monotonically increasing. Second one, n is monotonically decreasing. And the third one is n converges. D is n diverges to to plus infinity or minus infinity. Right? So this is my sequence, which is given by the recursive relation n plus 1 is equals to 3 plus 2 into an divided by 2 plus an, where a1 is equals to this. So what you observe is that try to that definition of monotone sequence. What is meant by monotone increasing? N is always less than or equals to n plus 1. Just recall the definition. What is monotone increasing sequence? You know the monotone increasing sequence. N always less than or equals to n plus 1. This is true for every n. This is monotone increasing, right? What is monotone decreasing? N is always bigger than or equals to n plus 1. This is true for every n, right? So neither happens means what? It may be oscillating finitely, oscillating infinitely. So use that idea and use the monotone convergence theorem. So you know a1, try to compute a2. So what is an plus 1? An plus 1 is given by 3 plus 2 into an divided by 2 plus an. 2 plus an 2 plus an, where a1 is equals to 1 for n equals to 1, 2, 3, 4 going on. So what you do is that when you're given a sequence in terms of the recurrence relation, just you understand that you need to apply the monotone convergence theorem. Understand? Suppose you're given a sequence, you are asked to compute whether monotone increasing or decreasing. What you do is that you just go back to your monotone convergence theorem. That is a fundamental argument. So in order to know that whether it is monotone increasing, whether it is convergent, whether it is something like increasing, decreasing, convergent. So what you do is that basically you apply the monotone convergence theorem. So first, in order to apply the monotone convergence theorem, I need to know that whether it is increasing or decreasing. So you know a1, this is my a1. Try to compute a2. So what is a2? 3 plus 2 into a2 over, this is a1. This is a1 plus a1, right? So 3 plus 2 into, what is my a1? 1 over 2 plus 1. That means 5 by 3, right? So 5 by 3 is always bigger than 1, right? Therefore, what is a1? This is a1. a1 is equals to 1. Therefore, what you observe is that a1 is always less than a2. a1 is always less than a2. So easily one can compute that my induction. I don't want to prove all the details. a1 already less than a2. So by induction, so automatically an is always less than or equals to an. An is always less than an plus 1 for every n. Therefore, what you observe is that this shows that n is monotone increasing sequence, right? N is monotone increasing sequence by induction, right? So there are two choices. Either it is bounded above, a sequence which is bounded above, or not bounded above. There are two options for the sequence. Suppose it is bounded above, once you prove that it is bounded above, automatically it is convergent by monotone convergence theorem. Suppose it is unbounded above, so again by the basic note, definitely diverges to plus infinity because it monotone increasing, and not bounded above, that leads to the sequence diverges to plus infinity. There are two possibilities, whether it is bounded above or unbounded above. Once it is bounded above, by Montan convergence theorem, it converges to some real number. In fact, it converges to its supremum. Once it is unbounded above, this sequence diverges to plus infinity because it is Montan increasing and not bounded above. This tends to, plus infinity. So look at the argument. So here, my A1 is what actually 1, A2 is what actually 5 by 3. So 5 by 3 is, what is meant by 5 by 3? 1 point something, right? 1 point, or 2 means 6 you are going to get. It's always less than 2. This is my idea. Of course, this is less than 3 also. Similarly, you can compute A3. What is A3? A3 is nothing but what? 3 plus 2 into A2 divided by 2 plus A2. That means what? 3 plus 2 into 5 by 3 divided by 2 plus 5 by 3. That means what? That means what? This is nothing but 9 plus 10 divided by 6 plus 5. That means what? 19 by 11. So 19 by 11 means what? Again, you are going to have actually 1 point something. Therefore, this is always less than 2. So again, what you observe is that A1 is less than 2, A2 is also less than 2, A3 also less than 2. Therefore, by induction again, An is always less than 2 for every n. Therefore, this is Montan increasing and bounded above. So therefore, by Montan convergence theorem, so I'm going to write big. By Montan convergence theorem, so An converges. An converges. So suppose you assume that it converges to some real number L. The limit is L. So I need to compute L, right? By Montan convergence theorem. So therefore, what you do is that just that An plus 1 is equals to what? An plus 1 is equals to 3 plus 2n, 3 plus 2n, 2n divided by 2 plus an for every n. So therefore, again, letting n tends to infinity, what you get? Letting n tends to infinity, what you get? By applying n tends to infinity, what you get? This limit n tends to infinity, an plus 1 is equals to limit n tends to infinity, 3 plus 2 into n divided by 2 plus an. Therefore, as I already told you, this is what tail, one tail of the sequence. A sequence comes to L, a sequence comes to L. Therefore, this is one tail of the sequence. Therefore, that every tail converges to L. We have seen. So this converges to L. So this is also quotient of the limits. So therefore, 3 plus 2 into L divided by 2 plus L. Because by tail, once the sequence converges, every tail converges to same L. You have seen. Therefore, by cross multiplication, 2L plus L square is equals to 3 plus 2L. Therefore, 2L cancel because L is a real number. We can easily cancel them. Therefore, L square is equals to 3. Therefore, L is equals to plus or minus root 3. Therefore, there are two options. Either L is equals to root 3 or L is equals to minus root 3. So, that actually limit of a sequence, once the limit is convergent, that means the sequence is convergent, limit always unique. We don't have two limits for a convergent sequence. So therefore, exactly one of the option will be there. L equals to root 3 or L is equals to minus root 3. We don't have two options, plus or minus root 3, because An is a convergent sequence. Every convergent sequence has a unique limit. Therefore, the very fundamental result, once the sequence, look at the nature of the sequence. What is the nature of the sequence? A1 is 1, A2 is 1.6, A3 also positive, A4 also positive. Therefore, what you observe? Therefore, by induction, An is always positive for every n belongs to n. Therefore, once the sequence is positive, En converges to L, there is a fundamental result, which I told you. Whenever the sequence is non-negative sequence, whenever the sequence converges to some real number, that limit also will have the same nature. L will be bigger than or equals to always 0. That means L should be non-negative. Therefore, here L is negative. Therefore, this is might not suitable answer. Therefore, what is my suitable answer? L is equals to root 3. Therefore, Ln, that means the given sequence is Montan increasing and the given sequence is bounded above and the given sequence is convergent. The limit is root 3. Right? So therefore, this is Montan increasing. This is the right answer. Not decreasing. And this is convergent. So this divergent is wrong. right? So this is also a nice problem, right? Suppose you take a second example. Suppose my sequence n is equals to, let my sequence which is given by 2 plus n minus 1 for n equals to 2 to 3 like this, and a1 is equals to like 1. So which of the following is true? So first one, n is convergent. Second one, n is divergent. Third one, n is monotone increasing sequence. Fourth one, n is monotonically decreasing sequence, right? So this is my sequence. Again, what I told you by previous for the previous problem, whenever the sequence is given in terms of the recurrence relation. So what you observe is just you keep in mind, that the theorem, well-known theorem, monotone convergence theorem. So it tells you that whenever the sequence is increasing sequence, monotone increasing, and it is bounded above, it converges to its supremum. Whenever it is decreasing sequence, it is bounded below, it converges to its infimum. And whenever it is increasing, not bounded above, it diverges to plus infinity. Similarly, for the divergent sequence, for the decreasing sequence. So you are given that n is equals to root of 2 plus n minus 1 for n equals to 2, 2, 3, 4 going on. You are given that a1 is equals to 1. So look at the, compute a2. So what is a2? 2 plus a1. Therefore, what is this? Actually 2 plus 1. That means what? Root 3. Root 3 is nothing but 1.713 like this. So this is always bigger than 1. But 1 is always, 1 is nothing but what? A1. Therefore, a1 is less than a2. So by induction, one can easily prove that an is always less than an plus 1. So this shows that n is increasing sequence. Monotonically increasing sequence. Right? Question is that is it bounded above or not? That is my question. So there are two possibilities. Either bounded above, or not bounded above. Not bounded above. If it is bounded above, so not bounded above. So we need to know that what is actually it is bounded above or not bounded above. So once you observe that a1 is what? 1. What do you know actually? a1 is 1. a2 is what? What is a2? a2 is nothing but what? Root 3. Root 3 is always less than root 4. Because 3 is, 3 is less than 4. But root 4 is nothing but 2. So again, we observe that a1 also less than 2. So a3 is what actually? Again, 2 plus a2. Therefore, a2 is nothing but what? a2 is less than 2. Applying this 2 plus 2, therefore root 4, that is nothing but 2. So again, by induction, n is less than 2 for every n. Therefore, n is monotone increasing and it bounded above. It is bounded above. Right? Therefore, by monotone convergence theorem, n definitely converges to some limit, real number. Therefore, the answer is over. Actually, I don't want to compute the limit. What you are given is that you are given, you need to find convergent or divergent or increasing or decreasing. Right? So therefore, this is convergent, not divergent. It is monotone increasing. It is not monotone decreasing. Right? Suppose you're given, what is the limit? First, suppose you're asked to compute what is the limit. So what you do is that you're given that en plus 1 is equals to what you're given? En is equals to 2 plus n minus 1 for n bigger than equals to 2. Again, this is true for every n bigger than equals to 2. Again, letting n tends to infinity. So limit of this is equals to limit of this. So therefore, limit is actually what? This is nothing but L. Again, you know that we'll see later, root is always continuous function. Therefore, limit of the square root is nothing but square root of the limit 2 plus n minus 1 is converges to L. Therefore, again, I need to find L. So therefore, squaring on both sides, this is nothing but 2 plus L. Therefore, L square minus L plus, sorry, minus 2 equals to 0. So what you get? This is nothing but L minus 2 into L plus 1 equals to 0. Therefore, L equals to plus 2 or L equals to minus 1. So the thing is, once the sequence convergent, we need to have a unique limit. We don't have two limits for a same sequence. So therefore, only one possibility, either this possibility, but you are with a positive sequence. A1 is 1, A2 is also, A2 is, root 3. This is also positive. A3 also positive. A4 also positive. By induction, An is positive for every n. An positive and, An converges to L. So again, by theorem, the limit also will have the same nature. Therefore, L must be non-negative. Therefore, the only possibility, this is not possibility. Therefore, L equals to 2 is the right answer. Right? This is also interesting example. One can easily, notice that. Right? Next is that third one. Example, n is equals to root of 3 into an, where a1 equals to 1. So which of the following is true? First one is that an is increasing sequence, monotonically increasing sequence. N is monotonically decreasing sequence. Third is n is bounded. Fourth one is n convergent. Is n is divergent. Either it diverges to plus infinity or minus infinity. Right? So again, you are given a sequence which is in terms of recurrence relation. Right? This is an plus 1. So this is my an plus 1. Right? So therefore, what you are given is a1 is 1, an plus 1 is root of 3 into an for n equals to 1, 2, 3, 4 going on. Right? So in order to know that whether increasing or decreasing, look at the second term. What is my a2? 3 into a1. That means 3 into a1 is nothing but 1. This is nothing but root 3. Again, root 3 is nothing but 1.7713 like this. But this is always bigger than 1. This is nothing but a1. Therefore, a1 is always less than a2. Again, easily one can conclude that it is by induction, n is always less than n plus 1 for every n. Therefore, this shows that n is monotone increasing sequence. Monotonically increasing sequence. So there are two options again, whether it is bounded above or not. There are two options, bounded above or bounded below. Not bounded above. Not bounded above. Right? So look at the nature of the terms. A1 is what actually? A1 is 1. A2 is what actually? Root 3. Root 3 is always less than root 4, but root 4 is nothing but 2. A1 is always less than 2. Similarly, A3 is nothing but what? A3 is nothing but root 3 into A2, but A2 is less than 2. Therefore, this is less than 3 into 2. That means, what is this? What is this? This is nothing but 6. Root 6 is nothing but, lying between, what is this? This is exactly lying between root 9. This is nothing but 3. Right? Yes or no? Therefore, this is less than 3. This is also less than 3. I'm going to write like this. I need to have at least one upper bound for that. So 3 is, I'm guessing that actually 3 may be upper bound for the sequence. What is my A4? A4 is nothing but 3 into A3. Again, A3 is actually what? Less than 3. So 3 into 3 is nothing but what? Root 9. This is always what? 3. Therefore, A4 is also bounded over by 3. So by induction, n is less than 3 for every n. So therefore, n is bounded above sequence. What you know? N is bounded above sequence. Above sequence. So therefore, by Montan convergence theorem, n converges to L, real number. Right? So in order to compute a limit, again same formula you're going to apply. So you're given that an plus 1 is equals to root of 3 into an. This is true for every n. Again, letting n tends to infinity. This is first to tail. This is equals to L. This is nothing but again sequence which comes to L. Therefore, squaring on both sides, what you get is L square is equals to 3L. Therefore, L square minus 3L is equals to 0. Again, L common, L minus 3 equals to 0. Therefore, L equals to 0 or L equals to 3. Therefore, what you observe is that again, all the terms you observe that A1 is what? 1. A2 is what? 2. Therefore, what you observe? All the terms lying between 1 to 3 for every n. Right? A1 is 1. A2 is what? A2 is 2. A3 is what? Again, root 6. Therefore, all the terms lying between 1 and 3. So therefore, you know, actually an converges to L. Again, by the theorem tells you that this limit also lying between 1 to 3. Right? So therefore, there are two options, either 1, 0 or 3. This is not possible because once you take L equals to 0, 1 less than or equals 0, this is impossible. Therefore, the only case is L equals to 3. Right? This is what by properties. Whenever the sequence lying between some real numbers, whenever the sequence converges to some real number, the limit also will have the same nature. Right? The limit will be 3. Right? Again, this is next one.